Okay, we are looking at integrals of vector valued functions, parametrics, and polar functions today. So this is like definite just BC material. For vector valued functions, realistically, we just take integrals component-wise. So let's do an example here. If I have the integral from 0 to 2 of the vector valued function t negative t cubed dt, you just take the integral of both of the components. So this is the vector of 1/2 t squared minus 1/4 t to the 4th from 0 to 2. Let's see, 2 to the 4th, or 2 squared is 4 over 2 gives me 2, and 2 to the 4th is 16 over 4 is going to give me negative 4. And then both of these resolve to 0 when I put the zeros in. So this resolves to the vector 2, negative 4. So you literally just take things component by component. Let's take a look at another example. Okay, so let's say I want to take the indefinite integral of the secant squared of t, and then t times t squared plus 1 cubed dt. Okay, so the first one is easy. That's just the tangent of t plus some constant. So we'll call it c1. And then, so I've taken the integral of that, right? So let's back that up a minute. I'm being a little bit quick here. I'm taking that this is going to be tangent of t plus c1, and then I have to take the integral of the second part here, because the component of the integrals is the integral of, or the integral of the components is the component of the integrals. Okay, so I'm going to leave the first part alone here for a moment, and I'm going to note that this is a u substitution problem. So I let u equal t squared plus 1 du dt comes out as 2t, which means dt is du over 2t. So I can rewrite this as 1/2 times the integral of u to the 3rd du, because the t's are going to cancel out. And you can check that if you'd like. So this is going to be tangent of t plus c1, comma, 1/2 times, let's see, that's going to become 1/8 now, right? U to the 4th plus some other constant. And then we sub back in, right? So I should end up with the tangent of t plus c1, 1/8 times t squared plus 1 to the 4th plus c2. All right, so there we go. Now note the two constants have to be different. So you have to have a c1 here and a c2 here, because those are not necessarily the same number. Okay, so parametrics, like vector values, are also done component-wise. So let's say we know that x prime of t is the sine of t, and y prime of t is t squared plus 2. Right, so this means that dx dt is the sine of t, and dy dt is equal to t squared plus 2, which means that dx is the sine of t dt, and dy is t squared plus 2 dt. So we're just going to take integrals of all of this, right? Oops. So this comes out as x is equal to the negative cosine of t plus some c1. right? And this is going to be y is 1/3 t cubed plus 2t plus some c2. And now I have the parametric equations that would yield those two parametric derivatives. That's pretty quick, easy, not too hard to work with. Okay, so the big problem here is dealing with polars. All right, so how do we visualize this? Well, when you're dealing with polars, you're envisioning some polar curve that's r, which is some function of theta. Okay, and we're going to bind this with different values of theta. So this would be like theta is equal to a, and this value out here is, that's ugly, is theta equals to b, and we want to find that area. So the way we handle this is just like we did with rectangles. We're going to, I'm going to use a little drawing tool here to help me. I'm going to partition this thing, right? So let's build that there. There we go. And let's build partitions. There's 1, there's 2, there's 3, so forth and so on. And we'll call this like Q. This will be theta 1. This will be theta 2. We'll call this one theta I minus 1. We'll call this theta I. Okay? And there can be any number of these partitions here. And what we're going to do is we're going to pick some value between theta I minus 1 and theta I. And it doesn't matter which one, because it is, this is ultimately going to go off to infinity, and we're going to call that theta I star. Okay, so I'm going to magnify that one particular piece. Okay, so here we go. We have theta I, we have theta I minus 1. There's like some part of the curve there. And down the middle here, we have theta I star. Okay, and what we're going to do is we're going to approximate that as a sector. Okay, so we're going to say that this is like part of a circle here. Okay, so in order to find the area of this space, I need to find the area of a sector. Okay, which means that you take however many degrees you have, or radians you have, out of 2 pi, and multiply that by the area of the whole circle, given its radius r. Well, if you look, this reduces, the pi's fall out, and I get x over 2 times r squared. So one of the good things about working in radians. Okay, so we're going to kind of deal with the sector that we drew there that went from I minus 1 to I. So that area of that sector is going to be theta sub I minus theta sub I minus 1 over 2, right? Because that's the distance we're going in radians, times the radius, which is r of theta I star squared, right? Okay, so this is just the change in theta. So this can be reduced to 1/2 r times theta I star squared delta theta, right? Because all of these deltas are going to be considered being the same. So the area of the whole region should be approximately the sum from I equals 1 to n of 1/2 radius theta I star squared delta theta, which is equal to, the area will actually be equal to this when I let this thing go to infinity. So this is going to be 1 to infinity of r theta I star squared delta theta. Well, we've known for a while here that if I represent this as going to infinity, this is 1/2 the integral from a to b, because that's what the theta start at, a to b, of r squared d theta. So this here is something to not miss. This is the formula that we use for calculating the area under a polar curve. The area is going to be 1/2 the integral from a to b of r squared d theta. I didn't want you to think that this dropped out of the air somewhere. It is something that you need to memorize for the BC exam, but you should at least know that it came from some math. Examples here. Let's say that I have the curve r equals 1 plus 2 cosine theta. Okay, and as this thing goes from 0 to 2 pi, you're going to find that it kind of goes around like this, makes a little loop, comes back around, and there we are at 2 pi. Okay, and what we want to know is what's the area of this little tiny inner loop. Okay, so the two places where this happens, these two crossings here, coming into the loop and out of the loop, are the two places where this thing, 1 plus 2 cosine theta, are equal to 0 on the interval 0 to 2 pi. Well, that means 2 cosine theta has to equal -1, cosine theta has to equal -1/2. And if you think about your unit circle, this is going to happen when theta is equal to 2 pi over 3 or 4 pi over 3. Okay, so to get this area here, this is going to be 1/2 the integral from 2 pi over 3 to 4 pi over 3 of 1 plus 2 cosine theta squared d theta. Now, that's a little bit of a challenge to work out. If this showed up on a test, they'd either have you stop there or they'd make it a calculator active problem. And if you make this a calculator active problem, you're going to get back 0.0543 is the area of that little teardrop region in the middle of that curve. All right, so let's look at one other one that's kind of common to the BC exam. Okay, so in this other one, let's say we want the area inside r equals 4 and outside 4 minus cosine theta. R equals 4 minus cosine theta. All right, so let's think about the graph here. The first one's pretty easy. This is just a circle that has a radius of 4. The other one is also a circle, and it's just shifted a bit. Okay, so the other one is a circle that's kind of shifted a wee bit this way. So the region that's inside this circle and outside that one is this region here. Okay, so we need to know where these 2 points of intersection are. So this is when 4 minus the cosine of theta is equal to 4. And we're going to take this on the interval from -pi to pi, because that will get me all the way around the circle. It's a 2 pi reality, but I'm kind of shifting it to the left, kind of making my math a little easier on myself here. So if I kind of move from here, I get negative cosine theta is 0, which means the cosine theta is 0. And on that interval, this happens when theta is equal to -pi over 2 or pi over 2. So what is my area going to be here? It's going to be half the integral from -pi over 2 to pi over 2 of 4 squared d theta. So that's the area of the whole circle, first circle, minus -pi over 2 to pi over 2 of 4 minus cosine theta squared d theta. So that's taking off. So between these two marks, what I've done is I've found this whole area, and I've found this whole area, right? And I've taken away this area, which is going to leave me back exactly what I want, which is this piece right here. Now again, too complicated to do by hand. Either they would have you just set it up and not solve, or they would have you do it calculator active. If you do this calculator active, that area comes out as 7.214 units, or square units. So there you go. There's your introduction to vector valued functions, parametrics, and polars with integrals.